calculus students. So this final video on finding the area between two curves is going to be finding area using subregions. So this topic is very similar to the method that we used up here in example 4. This had two subregions, and we had to use two different integrals because the top and the bottom function changed places. This problem is very easy to see that we had to use two different subregions because they are literally separated from each other. These problems are going to be a little bit different because it will be a little harder to tell how many subregions you might need to use, and you'll have to be a little bit more discerning with figuring out what is the upper and what is the lower function. So let's start with example 5. Let's move this thing up. Okay. Example 5. So I want you to start and just try shade in what you think is the region bounded by the graphs. Please pause me and shade in the region bounded by the graphs. Okay, so the region bounded by the graphs is this, because I can see it is inside of all three graphs. It's also this, because this is also inside all three graphs. It's also this. So the region bounded by the graphs is kind of like these three areas all together. So this full shaded region is what we're trying to find the area of. I'm going to use different colors to highlight my different functions so I can determine what's my upper function and my lower function. I'm going to make the upside down parabola yellow. I'm just going to make yellow the places that touch my shaded region. I'll make negative x blue. So negative x is this line with a negative slope. And then I'll make 4x positive slope pink. Okay. So now I think it's easier to see where my two subregions are. My upper function is always the yellow one, and from right here on this left, the lower function is the pink, and then to the right, the lower function is the blue. So I'm going to have two subregions. So I would determine these points of intersection basically the same way that we did before. I can set the yellow function equal to the pink one to find these intersection points. So I would set 12 minus x squared equal to 4x. Set it equal to 0. And factor. I get x equals negative 6 and x equals 2. I don't really care about this x equals 2. X equals 2 is this point over here, which doesn't really matter, but this one here at negative 6. So negative 6 is my left bound. And I can see pretty clearly these intersect at 0. So this first left integral will be the integral from negative 6 to 0 of 12 minus x squared minus pink function, which is 4x dx. And then I would add it with the integral from 0 to whatever this point is. If I set these equal to each other, we'd be able to tell. So I would set the yellow parabola and the blue function equal to each other. This point ends up being 4. So I'll just say from 0 to 4. The upper function is 12 minus x squared, and then the lower function is negative x. So it's minus negative x dx. Go ahead, put that in the calculator, figure out what you get. You should get 106.666666 repeating, so 667. Cool. This one's really similar, except you have to sketch the functions on your own. Gasp. So you can sketch while I'm sketching. I totally believe in your sketching powers. It's just a line and a square root. The line has a y-intercept of -2, so I'm going to just make sure to go all the way down to -2. Then 1, 2, 3, 4, 1, 2. So my square root, I'll do square root 0, 1, 2, like that. And then the line, it's like this. Wow, that was a bad line, but whatever. Let's see what I'm doing. And it also says in the first quadrant. So if I'm only looking in the first quadrant, I'm just going to look at this area right here. Okay. So it might be able to be hard to tell. Some of you might say, oh, the upper function is the square root. So square root is my upper. And then the lower function is this line. But when I highlight it, I hope you can see that that line doesn't cover part of our function. And so we also have to consider the x-axis right here. So this is how I have two different subregions. So I have the subregion to the left and the subregion to the right. Okay. I think it's easy to see that this goes 0, 2, and 4. So these are going to be my bounds of integration. Go from 0 to 2. Square root of x is the upper function, and the lower function is just 0. So it's like -0 dx. This is straight up just area underneath the curve. So it's the integral of the function. And then in addition to the integral from 2 to 4, the square root of x is still my upper function, and the lower function is now this line, so I'm going to put it in parentheses, minus x minus 2 dx. You can check. It should end up equaling 4.276. Then one more example. So this example is integrating with respect to y. In all our other examples, we've been integrating with respect to x, which has been when we've used the upper minus lower. But when you integrate with respect to y, so for instance, we have these equations that are solved for y, or solved for x. The variable is y. Okay. So when this type of deal happens, instead of upper minus lower, this is the scenario where you're going to use the right minus the left that we talked about a little bit. So here we'll use right minus left. And this comes in handy for different reasons. The reason why it comes in handy in this one is because if we try to use x values, so if I solve these equations for x, this square root function, this would be a positive square root and a negative square root, and I would have to create two different subintervals. So I'd have this subinterval from here to here, and then this subinterval here. So basically, it makes it easier to go left to right because it's just one interval. The right and the left stay the same the whole time. So it just makes it so you have to use fewer integrals. I think it's pretty nice. So I'll highlight this function here. 3 minus y squared is this yellow one. It's a sideways parabola. It's one equation. We don't need the two square root functions like we would if we solve for x. And then this line, y plus 1, is right here. So I have the same right and the same left. The one other thing that's going to be different is now our bounds of integration. So when I set up my integral, I'm going to write it over here. I have so much space. When I set up my integral, I need to make sure to use y values. So instead of x values, I'm using like my smallest y value to my biggest y value. And in this case, It's just this one is -2. So I could set these equal and solve for the points of intersection, and I would get -2 and 1. So it's -2 to 1. I'm using y values. The right function is 3 minus y squared, and the left function is y plus 1 dy. And your calculator allows you to type this in with y's. So you can do that. I think on the TI-84, you would actually type it in with x's, and it will give you the same correct answer. So because everything is in terms of y, frankly, the calculator isn't smart enough to know the difference. So if you just type in x, x, and x, but have everything the same way it is here, the calculator, it will calculate correctly. And we can talk about that more later if you have questions, if that's confusing, like why do I have to write y here, but I can type x on the calculator? It's because the calculator's dumb. But this would end up being 4.5, so you can check that. Biggest things here is that basically all your variables, so the equations are solved in terms of y. And then the bounds of integration are y values. Okay, I'm not sure how long that took. I hope it was less than 12 minutes. I'll see when I turn this off. But I just wanted to expose